Hello, everyone. Uh, I'm very excited to be here to talk about digital process intelligence in REPAM. We had some very nice, detailed, actually scientific talks. Uh, but fortunately or unfortunately, I am here mostly to talk about the overall activities in REPAM, which covers lots of things. And I have some logos here, but it involves all the partners. And there are lots of quite exciting activities going on. And of course, I will talk about the plans and what has been done, but these are all ongoing works. So yeah, I will just have the overview, and then you can always follow up more on the project and how it evolves. If I can go to next slide, yes. And yeah, so what I want to talk about, it's first general overview of modeling activities in REPAM, and what was the plan, what is happening, and what will happen, hopefully in the future. And then I will have three small examples on yeah, on the work that has been done. Yeah, so the overview of this work is that yeah, we all know this, and we also all these additive manufacturing processes, and also feedstock processing, mostly for powder, which involves atomization. And we all know all these atomization and additive manufacturing processes are very dynamic, can be very intense, very fast, and yeah, it's not maybe easy to monitor, optimize, and control with conventional methods. So we need lots of modeling, lots of either physics-based modeling or data-driven modeling to capture all the physics that is involved in these processes, and also control and monitor them. So the whole objective of the REPAM, especially in this dedicated work package, was to have and kind of like find suitable modeling approaches and develop them in a way that is suited the project. And these are more or less uh, involving material and process modeling and validation, integration of AI for material design, like we know what kind of materials we have in this project, but the chemical composition can be very critical. So we can use lots of physics-based or data-driven models for material design, and also enhancing our process monitoring and control. Yep, and as we saw in this very nice video in the beginning of the webinar, that we have before even going to the manufacturing itself, you have lots of feedstock processing, that a lot of waste can be happen during that. So one part of, if I want to roughly classify this, what REPAM is doing is, of course, first we need to consider this feedstock processing, which is mostly like powder processing, like gas atomization or centrifugal atomization, and also need to monitor, control, and predict the quality of the powder, mostly in the sense of particle size distribution and morphology, based on these intense processing parameters that are in during these processes. And yeah, of course, like we will use lots of physics-based modeling, like computational fluid dynamics or CFD, to get this very highly dynamic atomization processes. And also during this, like using lots of sensors that, again, we saw in the previous talks, we can gather lots of data that can be used and processed into a way to either control the process itself, or predict what kind of product we can get, and then based on that optimize the process to get like the powder that has lower waste, lower energy. It's more usable for the processes that we have. So of course, this is one side, and also after this, the manufacturing itself is also very important. To, again, because it's a very dynamic process, we need to monitor, control, and also predict the material behavior in order to see the defects or other things that we can see, especially like, for example, with the new feedstock. Like again, in the previous talks we saw in the REPAM project, there are what kind of new feedstocks like the wires and the powder cord or chip cord wires are developing, right? That of course there are many models that can be used for this, but can we really see that also for these new feedstocks that are these modeling approaches work? And again, here our approach is that we have for AM, as we saw, like there has been a huge work on modeling side, and we can kind of different models, like either on the powder, we can classify maybe on the powder scale and also on the part scale to see the temperature and the distortions due to the residual stresses and these things, or do some like Kalfat based modeling to see the phases that forms and the segregation and these things. And you also see some physics computational fluid dynamics models here. And also another approach is to use again this kind of data-driven approaches for materials modeling and material design, and also get prediction, and also have maybe a combined like physics informed machine learnings to use the data that we get from this physics-based modeling into this modeling data-driven approaches. So this is the whole picture kind of, and I know different activities are happening in these different areas. So, and unfortunately, there is not enough time to talk about all of this. And also, I'm mostly on a material science, material scientist, so I don't have much information about the machine learning and these things. But I will present this the whole work as a overview of the REPAM. And yeah, how this helps us, like of course we again saw like that we need precise control over the processes, especially the feedstock processing, to have a more high quality powder with reduced waste, and to reduce energy consumptions, and get a better yield of these atomization processes. And also we can use these models for understanding better, to optimize these processes. And also another goal is to extend these models to a broader maybe broader materials, like different kind of alloys and material and powders, and also feedstocks geometries or shape or compositions. So that's a whole overview. And I will have some examples, some of this work. I will start with some CFD modeling for laser-based processes. So hopefully, I can just explain a bit about these works and I can be clear. So as I said, this laser-based powder bed fusion or wire D or laser wire or powder DED can be very sophisticated, can be very intense and dynamic, and lots of physics happening there. Like you have laser and materials interactions. We can have some phase transformation. The easiest is like the melting and solidification, but also maybe some solid state phase transformation. And also lots of melt, pull, and liquid like dynamics, like surface tensions, Marangoni forces, recoil pressure. Lots of stuff is happening at the smaller scale, I would say, like the powder scale, like or a single track scale. And one of the good things with this approach, with the computational fluid dynamics or CFD approach, that you can see like the whole formulation, is like it can address many of these physics. So for example, you can see the forces, we can see the evaporation, surface tensions effects, all the liquid kind of and the fluid dynamics, and also like things related to heat transfer. So it can be very good for getting a better understanding of these processes, and also get like lots of useful information like temperature fields, for example. And there has been many of these works like CFD works around, and we know like but they have been focused more or less for like materials like itself, like I don't know, like steels or stainless steels or aluminum or titanium and these things. But in a previous study that we had, we tried to use this for um, alloy specific materials. Like, for example, this is for some magnesium alloys because they have lots of evaporation and it's very important in additive manufacturing of magnesium alloys. But it also it was a good example to see, even if the same alloying system, if you have like a few percent more zinc or like rare earths in this case, does it can it the model still capture this? And the answer was kind of yes. So we can see differences in how the, for example, in a keyhole mode, how the keyhole forms and how much different porosity and bubbles we get like during the processes, even with slight changes in composition, and more importantly, the evaporation of the whole element that can be related to evaporation and elemental loss in the actual part. Like if you want to print something with this composition, how much of this elemental, like this elements may lost during because of the evaporation. And that's why we chose this approach. And yeah, so for that to be happen, we need to have the chemical composition specific physical properties. So for that, we use some kind of CalFAD or method based in the thermocalc software, so we can get the temperature dependent physical properties that we can use this in the CFD mode. And then we have been able to develop this to a kind of like a fast pace, either in like you can see powder bed fusion or wire methods. And we can use this if this one works. Yeah. And then we can, of course, extend this to different printing strategies. Like, for example, if you are building a wall or you're building like a cube or like just tracks next to each other. And yeah, it can be used for that, and it can give information, important information like temperature distribution and these things. And also, these models are very much can capture the effect of different processing parameters like power, scanning speed, and feed rate. For example, if we see like how this can be uh, can be captured with changing the processing parameters. Of course, we have been trying to validate this somehow a little bit, but this is still continuing. But I would say it's going to a right direction. And also these materials, we can get lots of important information about how in a wall, for example, the temperature evolves. Because one single track is not only affected during like one single track deposition, but also when you put other tracks on top of it, it will still get some more different, like kind of like a heat treatment effect that can affect. Of course, this can be all useful for predicting the final microstructure, the final precipitates, and these things. Yeah. So this was mostly the work that has been doing, like both on, I would say, on wire DED and also laser powder bed fusion, mostly for copper alloys, that one. And they've been extending to the materials and feedstocks that are interesting in REPAM project. And also in another, like again, in this area, in the REPAM, there has been some physics-informed machine learning for first, like predicting this material printing, and also to use this further for alloy design. That use again this kind of like CalFAT based approaches, and also uses like the experimental data that has been that is available for this, and also to cover a more higher range of experiments, you can use the CFD or physics based modeling to inform these machine learning models. Yeah. And yep, just it was some activities on the manufacturing kind of part, and also there has been lots of work in REPAM for enhancing process control in either centrifugal or gas atomization models. Uh, I will just skip through this very fast. It has been lots of work, but and very interesting data, just to show it, and then yep, it's good to know what's happening here. And again, like what is mostly is has been used in REPAM is either gas atomization, that again we have a melt and like the gas flow that will break all this melt into the powder particles, or you can use a centrifugal atomization, that this melt will be uh, hit a disk that is rotating, and then this will splash kind of all this melt into the finer particles that will be solidified into the powder. But again, because it involves melt and it was very high speed rotating and these things, it's a very dynamic process. So it's very nice to be able to model this and also to use sensors, different kind of sensors for this. But when you use sensors for this, as you saw in the previous presentations, like you get also lots of data that needs processing, needs to be like modeled in a good way that can be useful and this thing. So there has been lots of activities around this, for example, for centrifugal atomization. Yep, as you can see, like for example, this is a nice slide that shows different kind of sensors. For example, we have a thermographic camera that can capture the temperatures, and also accelerometers that can see what kind of like vibration and these things this rotating disc has, or some acoustic emission sensors that can pick up maybe like sometimes in the we have like the rotation and these particles that are solidified into particles can hit the wall and can have different like acoustic signals, or maybe just drop. So based on that, maybe it is possible to also predict what kind of trajectory they had and what kind of solidification they go through and what kind of size they will have at the end, and also some high speed camera. So it's lots of different kind of sensors in this multi-sensor approach. Yep, and yep. So I have one example of this, how this can be processed. For example, for the temperature data, like you can see, like this is more or less focused on the center of the disk, and then it needs to be turned into like a feature that can be explored. So it's mostly based on this. We'll have like some ellipses that are fitted in here, and then based on what is basically needed is to kind of relate this to the stability or instability of the temperatures in this process. That, and then it can be related with these models into the final quality. So for example, for this, if you have the temperature on the disk, then this can be chosen by fitted ellipses, and then also into sections, angular sections, and then you can have like a heat map that is basically the time and also this temperature along the angles that along this or these angular temperatures that we can have. So based off this, this can be it can be like a measurable feature that can be like the instabilities of the temperature or just the general temperature levels uh, in general. And then there it has been tried to in this project to relate this into the final quality of the powder, which is basically the uh, size that is needed mostly for printing. And then we see very good correlation in this part. Yeah. And then the same thing that can be uh, basically be done for the other uh, sensors in a different manners that has been done in this project, or and also for the high speed camera that can be more problematic because it's mostly like a 2D, two-dimensional projection of a three-dimensional process. So it can make detecting the trajectory is harder, and also it's like very sensitive to processing. So at the end, we see that we can use this data in a very efficient manner to monitor the process and also control this. And based off this data that we get, we can have a stability or instability prediction and relate that to the final product. Yeah, and another example of this has been the for the gas atomization, that this one has been mostly to see the atomization parameters, the relation between the atomization parameters and the final product that has been during with the existing data that, for example, ERA still has provided, and they have measured this for years and years. And again, we can get lots of data that is like, as you see, there are dependent. What we have is like the temperature, gas to metal ratio, and also chemical composition, and also different things that it's a big kind of information that we can get from this kind of gas atomization processes. And then the modeling approach has to be to just use this feature, or just also to use some physical features, like for example, again, use the surface tension or other or viscosity or this kind of thermophysical features from thermocalc, and then add this to the feature that we already have. And then using that, it has been possible to see that, of course, like we can define different targets, like for example, like the finer range of the particles, or the coarser range of the particles, or the median particle size that we can have. And we see like in a modeling kind of approach, they are dependent differently, like the predictability and the accuracy of this prediction can be different for different parameters. And in general, we can also see that the addition or enriching this kind of data with thermophysical data from thermocalc, for example, can help to build a better model that can predict better, but not necessarily for all the parameters, like for all the targets that we see here. So this was the basic conclusions that we can get from this. Yeah, so I will finish here. I will just say some summary that, yeah, it was a very big picture of the project. Many are involved in this part, and the goal is to support all of the activities, like all of the experimental activities in this in REPAM that is like still going. So it was just implementation of the models and to see if they work, and then they will be used in future for all the activities in this very big project. And yeah, just a summary here that of course we all know that the data quality and consistency are very critical limiting factor, of course, but and also when we have like limited data, maybe we can complement this with physically informed like approaches, like using other kind of modeling or yeah, different kind of parameters that we can get. And from the other data, we saw that it is possible to use these methods for these multi-sensor approaches and get this data to predict the final quality that is needed. Yeah.
Thank you, Mohammed.
Yeah, thank you so much. Sorry if I took too much time.
Don't worry about it.
Yeah.